We were talking about the defense mechanisms to solve the race condition problem by using Java examples. We will first use the computing example to discuss how we defend against the race condition problem. We have the three same Java files as our previous example demonstration. The implement runnable scene.java remains unchanged. The run method calls the computing method of a present object. The daemon scene method in the race condition computing defense test class creates two runnable objects which share the same present object, and then create two threads and run. Please note that when the thread runs, it will actually call the computing method of the present. How can we synchronize to make sure that the two threads will not interfere with each other and only one thread will enter into the critical section when the shared count variable is updated? In this race condition defense example, we're actually using this synchronize this mechanism. Please note that this keyword is the present object itself, and in this case, it is also a lock object, an object level lock in Java. The synchronize this statement inside the method is simply trying to demonstrate the keyword synchronized and this object. Actually, most often we're not using something like this. Actually, the keyword synchronize is usually part of the method declaration as shown here, just before the method name and return type of the public keyword. So let's run this example. You can see the printout of the result: A is 12, B is 9, A is 12, B is 9. Now we see that the B is 7, A is 9. The printout are consistent. We only have these two results, no other result, such as A is 9 and B is 9, as shown in our previous race condition problem demonstration. This is one way for users to use the lock mechanism for race condition defense, the object level lock mechanism. Let's look at another example. Of object level lock. The example with the set name method. In the present class. As we can see, when we run the program, the running is the result is very consistent, and only the names of Lincoln AB and George Washington are printed out. The same reason, they synchronize this block has been put inside the same name method, which will make sure that only one thread will enter into the critical section. Here, so we'll be able to update the name at one time. In this way, it will make sure that the critical section will not be interleaved. Let's look at another approach, the fine-grained lock mechanism. Here we define two objects. We create two objects, log1 and log2, and then use these two logs to control the setName method and the getName method separately. And then for this method, we have to put synchronized log1 and synchronized log2 inside their corresponding methods. The results with the calling of setName method as you can see here are the same as the object level lock mechanism. They are consistent. Lincoln Navy, George Washington. One thing we really need to discuss here, since the setName method and the getName method use different locks, they do not affect each other, which means that the program should have a better performance, since now the two threads may have less opportunity to wait for the same lock. The problem is that we really need to be careful. The setName method and the getName method may still be able to interleave with each other on a single CPU, and thus the getName method may retrieve partially updated shared object status. Now we will talk about the semaphore mechanism. The rest of the program is the same as the code in our previous example. The only thing different here is that we define the semaphore test method to replace the setName method in our previous example. In the semaphore test method, the thread A with the ID as 1 will first compute for the object level log, and then wait for a semaphore to read first name and last name by calling the getName method and print out. Thread B with ID as 2 will compete for the same object level log and will set up the names. First name, last name. After that, thread B will notify all threads who are waiting for the semaphore. Let's see what is the result. Only Lincoln AB is printed out. Why? Because thread A will always wait for thread B to release the semaphore, while thread B updates the present object with Lincoln AB as the first name and the last name. In this way, the two threads are not only exclusive to enter into the critical section of accessing the first name and last name, but also are synchronized to ensure that the thread B runs before thread A. That's why we will always get Lincoln AB, since thread B is the thread to update name as Lincoln AB. Now, let's look at the software solution to solve the race condition problem. The implement runnable sync class and the race condition test class remains unchanged. The president class no longer has the set name and get name methods. Instead, it defines Peterson 6 method and the Peterson 7 method, which implements the classic Peterson solution 6 and Peterson solutions 7 respectively. Let's run this program to see if it works. In the implement runnable sync class, we will call the Peterson seven of a present object. We received consistent result of Lincoln AB printed out by thread B and George Washington printed out by thread A, as you can see here. It is worth it to note that using a software solution to achieve the mutual exclusion may have less performance penalty since it does not use computing resource, lock or semaphore. So this is pretty much about the race condition defense mechanisms, including object level lock, fine-grained locks, semaphore, and the software solution.